Well, if anyone has questions, you can go ahead and ask. I can answer questions before class. We got about 2 minutes left to do that. And also, if anyone wants to take a look at the solution of today's lecture, that we can do as well. So, Okay, I'm going to assume that yes, please is referring to the homework assignment. All right. All right. So there are some questions about question number 4 of the lab that's due tonight. Okay. So we can definitely talk about that. I'm going to go there to get ready. And I think most people are specifically asking about question number 4. All right. So we got about 20 seconds before.
So if you hack somebody's account and you post it on Twitter, they will take that then.
I guess somebody's mic is on. Was on. Oh. Nope, mine is just Costco coffee. Yep, I figure it's about 15 cents per cup or something like that. So it's definitely. Oh no, mine is black. Just black coffee. Nothing. There's nothing in it except for coffee. Oh yeah, I mean just the first taste of it, is gonna give me a jolt already. So that's the kind of coffee that I want. All right, so let's go ahead and get started with question number 4. And so we'll start from the beginning here because I want to explain what the question is asking. All right, so first, copy the following code to a text editor. Notepad should be fine. So you can use any text editor for this purpose. Next, change the byte directive after the definition of the label ID. So we are referring to these byte directives. If your student ID is 1562470, then the digits should be specified from top to bottom in this order. So basically just spell your student ID backwards. Also notice the JXI instruction. So the JXI instruction is right here. This is of course a placeholder. Your task is to change JXI to one of the 5 conditional branch instructions: JXI, JLI, JCI, JOI, JZI, JLI, and well, you get the idea. We got the 5 flags. So that the no-op instruction, no-op instruction at label L2. So we are referring to this specific no-op instruction right here, would execute the most number of times before the program reaches the halt instruction. So there's only one single halt instruction in this case. You cannot change the program in ways other than changing the JXI instruction and the byte directives. So the byte directives, you have to use your student ID, and then the JXI instruction, you have to change it to one of the 5. In the following space, write down which conditional branch instruction you choose and the actual number of times that the no-op instruction at label L2 executes based on your student ID. So the idea is you got 5 choices, but you have to choose the one that will give you the most number of execution of the no op instruction at label L2. So that is basically what the question is asking. All right. Green tea. Okay, so I'm taking it that everybody is understanding what the question is asking. So in other words, if you change this JXI instruction to JCI, how many times do we get to the no op instruction at label L2? If you change it to JZI, how many times do we get to the no op instruction at L2? If you change it to JLI, how many times do we get there? JOI and then JLI. Okay, so unless you can analyze the program and figure out everything theoretically, which is possible. I do not expect people to be able to do that right now at this point, but I think given all that we have talked about so far, that is actually possible. Okay, this program does not introduce any opcode that is new to us, except for maybe compare CMP. But even with that, given enough time, a person who is given the logisim file for the TTP and also understanding the working of the ROM can actually figure out the entire program, and without having to run any simulation. But the idea is I want you guys to run the program in Logisim. Basically, you have to run it 5 times. Each time, by changing the JXI instruction to one of the 5 conditional branch instructions. And the idea is also to kind of make you guys think about how do I log the execution of a program so that I can count the number of times that the no op instruction at label L2 executes. So there are so that's basically the intention of this assignment, is really to get you guys to use Logisim and to practice how to log the execution of a program in Logisim. All right, so let's go ahead and do this. Okay, I'm going to do this particular assignment, and let me look up the command to run to get Logisim to start. And let's see. All right, so there we go. All right, so here's Logisim, and I am going to run it, inside Logisim itself instead of using the trace analyzer. The trace analyzer is super handy. Okay, if you ended up using the trace analyzer, good for you, because I think it's really good to learn how to use the trace analyzer. On the other hand, if you basically say, okay, that seems like a lot of trouble, and I don't want to do it that way, not yet. Okay, but it's okay. That's perfectly understandable as well. So the first thing we need to do is to copy this program and put it into a text file. So I am just going to copy the whole program, select the whole thing, Control C, and put it into a program. And I will do everything on the command line, okay, which is kind of what I usually do. Okay, I don't use GUI too much, so I'm just going to do everything on the command line. This is using Linux, so if you use Windows, the commands will be slightly different. So we want to save it into, let me see how I should call this. Okay, JXI is fine. So we'll put it into jxi.ttpasm. I'd like to use the extension ttpasm to store the source code of the assembler, because this way I know what the file is, even though it really is just a text file. And then what I'll do is I also want to show you if you use VI. Now VI is not really for everybody, especially at this point. But on the other hand, if you think that you want to learn how to use VI because it is a very handy editor to use, you can go ahead and try to get into it. One nice thing about using VI is I have syntax highlighting tools just for VI. So with that tool, okay, when I edit a file with the TTP ASM using a VI variant, okay, so VI is visual, that's why it's called VI. VIM, is VI improved, and then NVIM stands for neo, which is new, VI improved. So, so it's basically a relatively long path of evolution, in this particular editor. So one thing that's really good about this editor and the syntax rules that I have written is if there's a syntax error, it will detect it and highlight it in red. So it stands out like right there, okay? So what I'll do is I'll also insert the word to do, okay? And the word to do, I think, is going to be highlighted too, once I fix the syntax error. So my recommendation is to change the instruction in a more systematic way. In other words, you want to use I would use alphabetical order, start with JCI. So you can see how to do is, it remains to be highlighted because that's actually a kind of important bookmark for me. I need to come back to here to change it. ID end isn't orange. That's because it is actually correct. There's no error with ID end. I'm not sure what Aiden is referring to, because ID end is a proper label. It isn't highlighted as a label at the top. Oh, I see what you mean. Yeah, it is. It's sort of highlighted, like cont and done, those are all labels. So they're all labeled correctly. Yeah, it is just blue, but it's so are the references of the other labels. The definition of labels are in a different color, but the references of labels are just like that. And the reason why it is like that is because anywhere a label can be referred to, you can also type in an entire expression. So that's why it is not highlighted in a very visible way. Yeah, it's about it's a little bit lighter. Yep. All right, so we got the program done, and now we need to utilize the assembler. So within VI, for those of you who are interested, within VI you can actually export the entire content without leaving the editor. You cannot just do a Control C, and then a Control A and then a Control C. That doesn't work. But there's another way of using the command line to do it, and I think you specify the start and the last line, and then you have to specify that you want to write to the clipboard. And I just can't remember how to do it. So sometimes I forget how to do certain things, and it's muscle memory, and I just cannot remember how to do it. So I'm gonna have to do it on the command line. Okay, so on the command line, we just do this, and then pipe it to xclip-cell clip. So what this does is it will copy the content of the file into the clipboard. And once I have everything in the clipboard, I go to the assembler. And since the assembler, this is the assembler that you guys have access to, so you can actually take a look at it too if you want to. But it's nothing exciting at this point, because all I did was to replace the JXI instruction with JCI. And everything seems to work. You go to the RAM file tab, and you click File, Download, comma separated values, and then you save the file. Okay, so when I save the file, I can save it as jci.csv. Okay, and now everything is good. Now we can switch to Logisim and get ready to run the program. So we right click, load image, and then go to where I saved the file. Oh, I forgot whether I put it into the temp folder or not. I think I might have forgotten to specify the temp folder. So we'll give it a try. Nope, okay, I did. Okay, I did specify the temp folder. So now the program is in. Now, if you run the program like this and just go to simulate and then turn on your tick enabled, and also to do this, you might want to change your tick frequency all the way to 4.1 kilohertz, because I think one person reported that it did not stop after like 10 minutes. That may be the case if the tick frequency is low. So if the tick frequency, I think the default is like 1 hertz or something like that, then it would take a long time for this program to complete. So you definitely want to increase the tick frequency all the way to 4.1 kilohertz to do this lab. All right. So if I were to do that, I would not be able to tell, or I would not be able to count how many times the instruction at the label L2 executes. So the best way to do it is to kind of use the logging capability. We talked about this in, I think a week ago, when this assignment was released. So we go to logging, and there are a few things that are particularly handy to log in this case. One is the program counter, and you can choose either one. You can use the register or you can use the output pin. They should be the same because the content of the program counter register is presented to the output pin all the time. So you can pick either one. So I just pick the register. And the other pin that is going to be very helpful is going to be, I think last time I also talked about this. It is the opcode fetch output pin, which is this guy over here. OP fetch is particularly important because we might step on a memory location, but without actually executing it. Okay, because when the program counter auto increment, for certain instructions, you might step on a location in RAM, but you're not actually executing. You're not going through the fetch decode cycle at that location. There's a question in the text channel. Oh, right. Okay, you guys cannot see it because it's above your viewport. There we go. All right, so we also want to change the program counter to base 16 because it's because eventually you have to match the program counter value to the location where the no op instruction is located. Now, base 2 will work if you want to do the conversion yourself, but since we can change the radix to base 10 or base 16, might as well just use base 16 because in the assembler, I think column W does display the address in hexadecimal or base 16. So that's a handy base to use. So I think these two are the ones that we need to use. And I personally would put it into a file instead of using the window or the table inside Logisim. So I would put it into a file, and I would specify that file to be in the temp folder and then jci.log. Okay, the extension really doesn't matter because it's just it really is just a text file. And I click save, and then we can now close this particular window. And now it's time to run the code. So we go to simulate. Make sure tick frequency is all the way up to 4.1 kilohertz, and then we click or enable ticks. There you go. And when you see that the RAM doesn't seem to be doing anything despite the clock is still ticking, that usually means we have gotten to the halt instruction already. And you can confirm that by looking at the halt pin. If the halt pin is a 1, that means we are at the halt instruction. So now we can stop the simulation. Okay, so we can disable ticks enabled. And now we have a text file to look at. So let me go to the text file right here. And we just take a look at, I think it's jci.log. And you can see, the program counter has its own column, and then OP fetch has its own column as well. So now we need to locate the address of the no op instruction. So to do that, you go back to the assembler and go to the assemble tab, use column W, and look at the source code. The no op instruction that we're interested in is this one. It has an address of 16 in hexadecimal. That is not 16, it is 16 in hexadecimal or 22 in decimal. So now we go here and we just have to count. Okay, we ask, okay, do we see 16? So we see 16, but you only count it as 1. Okay, because it shows up as 3, it's 3 entries, but the instruction is only executed once, because you can see only one of these rows has, OP fetch being a 1, like so. And then you look for other ones. Okay, that gets a little bit harder to see. Okay, so the best way to look at it is to look at the line number. So this is line 41. This is line 81. This is line 122, 163, 204, and so on. So I believe it is going to run 6 times in this case. So JCI would run exactly 6 times. Well, okay, I should say, I take it back. When JXI is JCI, we get to the no op instruction at label L2 exactly 6 times. So does that kind of explain how we can get to the answer? Okay, we got some questions coming. Alright, so the comment or question is, it only logs when something changes. So if you just log PC, then you only see each number once per execution. In this particular program, that is the case, but it is not necessarily that you want to count every time that the program counter gets to 16, because it depends on what is before that instruction. And in this program, it works because the instruction right before that is a branch instruction, so there's no way the program counter can auto increment to 16, and that's why it works also like that. Okay, and then we have 2 more people typing. So this is another thing that I want to show, because VI can do this. It's called regular expression matching. So you can basically type, okay, I want 16, and then I want any number of space, and then after that a 1. Okay, we talked about regular expression when we talked about base 10 scientific notation. So now I'm zeroing into having 16 in the first column and 1 in the second column. So this way, when I count, it's pretty easy. So this is 1, 2, 3, 4, 5, 6, and then we get back to the first one. So there are 6 distinct lines in the log that indicates that the no op at location 16 executes. All right, so back to the text area. One question is, how would we have done this if we weren't using the terminal? Not sure what you mean by that, because I was using the terminal only to edit the program. You could have used Notepad to do it. There's nothing else that I use the terminal for, other than starting up my editor. In other words, if you don't want to use the terminal, okay, let's put it aside. I could have just used Mousepad as an editor for everything. So I go to Mousepad. You still have to do the counting. Unfortunately, you have to do it by hand, but it's doable. Okay, and just so that you guys know what I'm talking about, so we go to temp, and then we have jci.log, right? So it's just a text file this time. And how many lines do we have in this file? It's reasonable. You can still do it by hand, or you can put it into a spreadsheet and use a spreadsheet function to count it as well. And then the next question is, but we just count when OP fetch is 1. Is that correct? So the way I set it up, the answer is yes. Okay, so when the program counter is 16. Okay, where is it? Up. There we go. So when the right here on this line here, so when the program counter PC is 16 and OP fetch is 1, then you count it. But this kind of goes back to why it is important to look at OP fetch, because it indicates that the location is accessed. It's accessed, but it is also in the fetch cycle of an instruction execution, because you can step into a particular RAM location but not execute the byte at that location. I'll give you an example here. Look at location 1, 2, okay, right there. So when you look at location 1, 2, do we get to that location in RAM? Yeah, absolutely. I mean, otherwise there would not be an entry in the log. But when you look at OP fetch, it remains 0 when that location of RAM is pointed to by the program counter. So you don't want to, so that means, the byte at location 1, 2 never executed, okay? We did get to that location, but it was never executed, and it's very important to make that distinction. So this is kind of going back to Aidan's observation of, in this particular program, you could have just logged the program counter, because every time we get to location 16, we ended up getting through the fetch cycle. But it is not fireproof. Okay, so if you want to be fireproof and want to say, okay, I only want to count the number of times I execute an instruction at a particular location, then you need to take a look at the OP fetch value and not just the program counter value. All right, so the next one is using Control F to search. Okay, that is correct. That is probably a common hotkey for search. Okay, so you can do it in mousepad, you can do it in notepad, you can do it in just about any editor that you probably encounter. Okay, and the next point is, and is this result different when we have different ID? Yes, absolutely, because it depends on the comparison of adjacent bytes. So depending on your specific ID, those values can change. And Aidan says here, why does it go to location 1, 2? Oh, that's easy. Okay, so let's try to figure out this mystery, because we got to location 1, 2, but we never executed the byte at that location. So now the question is, so what is going on here? Now, we did execute the opcode at location 1, 1, so that would be a clue to answer the question. So now we go back to the assembler, and then we go to location 1, 1 to try to figure out what that is. Location 1, 1 is in hexadecimal, so this is location. So if you remember the very first, one of the very first lab related to the assembler, I asked you guys to figure out, in this case, what is at location 1, 2. This is location 1, 1. This is location 1, 2. So we got to location 1, 2 because we want to use what the program counter is pointing to update the program counter itself. So that's why it shows up in the log. The program counter did get to location 1, 2 because we were there to grab this byte of 16 so that we can end up at location 16. That's why location 1, 2 shows up with PC being 1, 2, but we never executed this byte 16 as if it is an opcode. So I hope that explains how we got to location 1, 2 and why we did not execute the byte at location 1, 2 as if it is an opcode, because it is a part of a 2-byte opcode in this case. All right, cool. Any other questions related to this lab? So basically it is just a matter of changing the program. So basically after you count JCI that has executed 6 times, then you go back to this location, change JCI to, well, you don't want to change it in assemble, you have to do it in the source. But the idea is to change JCI now to the next one. Since I'm going alphabetical order, the next one should be JLI. Okay, let me take a quick look here. Yeah, so JLI would be the next one, and then you do exactly the same thing all over, and then do the counting. Then you move on to JOI, and then JSI, and then JZI, and then you just say, okay, based on all the counts, which one has the highest count? And I'll give you a clue. JOI would always be 6. Okay, There might be other ones that will tie with JOI, but JOI is always going to be one of the instructions that will give you the most number of times that we get to the no op instruction at location right at L2. All right. So I'm going to give you guys a few seconds, to ask any additional questions about this lab, both in terms of the concept and also in terms of the process. Okay, what tools did I use to do this, and how I got it done. And so you have I'll give you guys a few seconds to do that, and I'm going to move on to the next topic. All right. I'm not seeing any questions in. Oh, there we go. Aiden asked JOI since you never add to get. Well, it's about the compare, Aiden. It's about the comparison instruction. So when you go back to the assembler or go back to the source code, the conditional branch instruction, the JXI instruction, is right after a compare. A compare is basically a subtraction. So because none of the digits that we are subtracting should cause an overflow, so that means we should never execute an overflow, a JOI would never branch. And if it never branches, then it will go to JMPI done, and JMPI done is going to go to done, which is, oh, no, I take it back. I think I changed the wrong, I'm referring to the wrong one. It's this one over here. Sorry. Okay, so it is this comparison and it is this JXI that we are dealing with. And Aiden is correct. If the bytes down here, if it's 127, with one, and then the other one is, let's say, let's see, we want it to overflow, so we want to have negative 128 and then a 1. Okay, if you subtract 1 from 128, it's going to cause an overflow. But because these are digits, right, each digit can only go from 0 to 9 from your student ID, so it will never cause the overflow to happen. Because the worst we can possibly do is 0 minus 9, which is negative 9, which is way within the range of what we can represent as a signed value given 8 bits. So that's why the JOI would never execute. It would never. It never gets triggered, and as a result, we always end up at the no op at label L2. It depends on your actual ID. If your student ID has alternating, it doesn't have the same okay, let me see how I should put it. If your student ID does not have consecutive repeating digits, then JZI will never trigger as well. And as a result, your JZI instruction will also give you a count of 6. So, so JOI is a safe bet, but with the other 4, okay, it all depends on your actual ID. And oh, by the way, coincidentally, I think in this case, JCI and JLI would always give you the same count too. All right, so there are no additional questions. Okay, yeah. So with ON, the JZI can work. Okay, if your student ID does not have 2 or more consecutive same digits, then JZI would also give you a count of 6. That's entirely possible. But we should never get a count that is more than 6, okay? Because the entire the loop that is built in here will only execute 6 times. So we should never have a count of more than 6. Up to 6, yes, but not more than 6. All right, so we are now formally, technically, in assembly language programming. Finally, right? I mean, we're finally getting into the programming part of this. I'm not going to talk about this particular link here, setting up NeoVim with TTP-ASM syntax highlighting. For those people who are interested, go ahead and read it and try to set it up. But it's definitely something that is outside of the scope of this class. Okay. Now, why do you want to do something that is outside of the scope of the class? Because it will give you syntax highlighting that makes it kind of more convenient to locate syntax errors. So it can be a time saver, but it's only a time saver if you're proficient with VI and know how to set it up. So I would just kind of leave it at that. Okay. So now we're moving on to compiling C control structure, as a module. Okay, so this is a kind of an interesting module because it talks about how do we convert C control structure code, or structured C code, I should say it like that. How do we convert structured C code into TTP-ASM code? Most people would look at this and go like, whoa, wait, hold on a second here. They're not even close. Okay. Well, that's why it is worth talking about. And this is a module, just like the other modules. All right, so this one starts with control structures that we are familiar with. So in this case, we are talking about conditional statements. So when we see something like this as a conditional statement, the first question is, okay, what is C? C is really just a placeholder of a condition. In other words, C itself is not a variable. It is not a condition itself. It is a placeholder of a condition. So C basically would evaluate to a scalar that is either 0, which we consider false, or a non-zero, which we consider true. Okay. And then block 1, BLK1, is also not a statement itself because there's no such thing as block 1 in C or C++. So block 1 is once again a placeholder of what we want to do when the condition is true. And then block 2 is what we want to do when the condition is false. So this is a fairly, I hope everybody can get, would understand this control structure because it is very common. Basically all programming languages has conditional statements like this. And what we're going to do is we will translate that, continue to use C code, but it's going to look ugly like this. Okay. So this ugly code here has, a go-to statement, and it also has label definitions like L1 and L2. So label definitions are the ones with a name, which is a label, and then plus a colon. That you might say, but that looks like a label definition in my assembly language. You will be correct, okay, because it looks exactly the same. It is the same. And then the go-to is the same as a JMPI instruction. It is an unconditional branch instruction. In other words, if we get to this go-to, we are going to continue execution at label L1. In other words, we're going to execute block 2. So this part also relies on the fact that we understand how C syntax works. Okay, so just to make sure that everybody understands C syntax, even though you should have taken CISP310 already at this point, I still want to make sure. Okay, so we're gonna take a look at a snippet of code. This is not a complete program, it's just a snippet. Let me see. Well, I might as well just use an actual C program to illustrate this. So yeah, I changed my mind again. Let's go to online. Let me go to onlinegdb.com. Okay, really kind of cool place to kind of write sample programs, right? And we'll just say we have a local variable and it is called x. We'll initialize it to say 23. Okay. And then we're going to have a conditional statement. So I'm going to say if x equals to 23, then we print x is 23. Okay, so it's not really kind of that exciting, right? I mean, this program has a very well-defined behavior. Well, even though the web behavior is well defined, we still want to make sure that that is how it is going to run. So we'll go to, we first select the language. It's a plain C program, not even C++. And we go to debug, okay? And then we put a breakpoint on line 14, just so that, we run the program and we have control over, single stepping. So we run the program with an R. And not surprisingly, okay, we get to line 14. And the next line, that we are going to execute is quite obviously line 15, because x really has a value of 23, and we can confirm that by printing x. It is indeed 23. So when we single step, not surprisingly, we go to the printf statement. Okay, so right here, you can also follow the green highlight. So we are now going to print x is 23. So I'll just do a C to continue the execution of this program all the way to the end, because hey, it's not very exciting. All right, so let's make this program slightly more exciting. So in addition to saying printf, okay, I also want to say, yeah, this program is boring. Okay. Because it really is. Well, or is it? So this is where people would go like, from the perspective of indentation, it would seem that line 15 and line 16 belong to the same block. But in terms of the actual logic of the program, line 16 is actually not a part of the conditional statement. Well, there's only one conditional statement, so I don't have to say which one, right? But line 16 is not a part of the conditional statement. And then some people would complain and go like, yeah, but this would become a syntax error, right? Because we're specifying more than one statement without using the braces, to make a block statement out of this. Well, let's take a look. Okay, we'll go to, and this time we're gonna change x so that it is compared to 22 instead of 23. So now we go to debug. Okay, the breakpoint is still here on line 14, which is what I need. So we go to line 14 again, and when we single step, okay, most people go like, okay, first of all, I think some people may be surprised that the program actually compiled, okay, because it does not seem to be syntactically correct, but it really is syntactically correct. I'll explain that later. So what is kind of interesting is when I single step, where is it going to go? I don't have an else corresponding to this conditional statement. So that means, it's going to go to the end and continue after the conditional statement. So now the question is, where is the continuation after the conditional statement? Is it on line 16 or is it on line 18? Single step. Oh, it is on line 16. So line 16 it is as if this is specified after the conditional statement. Okay, so when we continue the execution of the program, it prints, yeah, this program is boring. Not, right? It is not boring because, I think it does not match the expectation of some people. So from the, okay, I'm gonna wait until Daniel is done typing. All right, so C doesn't care about white space, so I could have written the entire thing on one line and it would still have the same meaning. That is correct. So that's why the indentation in this case is fooling some people to think that line 16 is actually a part of the conditional statement. But now the question is, why is it not a part of the conditional statement? And if it's not a part of the conditional statement, why doesn't the compiler complain about it? From the compiler's perspective, the moment it parses the word if, then it knows what can potentially happen. It knows that whatever is immediately after the if has to be an expression that has to evaluate to some kind of scalar, and it has to be in parentheses. That part is mandatory. It's not a problem. And then when the compiler is right here at this moment, in other words, it has found the condition and parsed the entire expression for the condition. Right now, at this point, the compiler expects one single statement as the then statement. Okay, so, and that's exactly what it's going to find, because this particular printf statement is a statement. It is a function call statement, and it is a statement. So from the compiler's perspective, when it gets to this blinking cursor position, the compiler says, okay, I am done analyzing this conditional statement. I have found the end of the conditional statement, because the next thing is not an else. So I have found the end of the conditional statement, because it is only expecting a statement, a single statement after the condition. Which means by the time it gets to this particular printf statement, the compiler says this has absolutely nothing to do with the conditional statements, the conditional statement that I have already parsed and finished. This is after the conditional statement. So in other words, it is as if this printf statement is actually indented like this. If I want the indentation to reflect the nesting of the code, this would be correct. All right, so there's I thought there was a comment in the text area, but I am not seeing it. Okay, so, all right. All right, so what does this have anything to do with what I am trying to explain? So in the module, okay, so this go to L1 is the only then portion of this entire if statement. Now I decided to put the go to L1, on the same line as the if, because it is now becoming a conditional branch, okay, just like the JXI instructions. But we don't know what the condition is, so that's why we don't call it a conditional branch. But the point is, go to L1 as a statement would execute if and only if the condition of not C is true. If not C is false, it's going to fall through to block 1. So block 1 is not a part of the conditional statement. Block 1 is a statement or a chunk of statements that is right after the conditional statement, which is contained on one single line. Okay. So now we want to look at this code, the original C code, and we want to look at the ugly C code, and at least we want to see if they are equivalent. Okay. In the original code, if C is true, then we end up executing block 1. So we want the other code to have exactly the same behavior. So when we go to the other code, C is true, not C is false. If it is false, we are not going to go to L1, which means block 1 is going to execute. So far so good, but we are not done yet, because after block 1 is an unconditional branch to go to L2. So we are skipping block 2 in order to get to the label L2. So in terms of the behavior, when C is true, the original code and the converted code would behave the same way. Now, what if C is false? If C is false, then we get to execute block 2 in the original code. In the modified code, if C is false, then not C is going to be true. Then we end up executing the go-to statement, and we continue execution at label L1. But at label L1 is block 2. After we execute block 2, then we just continue with whatever is next to this block of statements. So the behavior is identical to the original code, even though it looks uglier. So I want to make sure that there's no question about the equivalency between the original structured code versus the ugly code, which I call the flattened code, because it doesn't have structure anymore. So I'm going to give you guys a few seconds to ask questions, or simply to let me know that you need more time if that is what is needed. All right, so there are no questions. I am going to assume that this part is understood. All right, now if this code compiles, okay, if I have syntactically correct condition C, syntactically block of a chunk of statement called block 1, and the same for block 2, if this compiles, guess what? This one would compile too. In other words, we're not quite translating into assembly code just yet. Okay, we are still staying in C code, which also means you can still continue to use online GDB to debug the program. Okay, in this transition. Next, we're going to take a look at pre-checking loops. Okay, with a pre-checking loop, usually it looks like this. Okay, and the way we translate that is going to look like this. So with a pre-checking loop, we first evaluate the condition. If the condition is true, we perform an iteration. Then we go back and check the condition again. So we keep doing this until the condition becomes false. Then we get out of the loop. So the other code, or the flattened code, looks like this. And in here, we also check the negated condition first. If the negated condition is true, which means condition C is false, then we go to a label L2, and the label L2 is after the unconditional branch to go back to label L1. So it mimics the behavior of the original code. What if C is true? If C is true, not C is going to be false, and as a result, we are not going to go to label L2. If we do not go to label L2, then we fall through to execute block 1. After block 1, we have an unconditional branch of go to L1. So we basically go back to the beginning, and then we check the condition again to see if the next iteration is needed. And that is also consistent with what a pre-checking loop or while loop is supposed to do. So that is why now we kind of know that the original code, structure code like this, can be translated into basically flattened or ugly code like this. So once again, I'll give you guys a few seconds to ask questions or ask for, a little bit more time to process this. If I don't see anything, I will continue on to post-checking loop. Alrighty, nothing. All right, so let's move on to post-checking loop. So post-checking loop are the do-while loop. Personally, I think the way I use loops are at least 90% pre-checking and maybe 5 to 10% of post-checking. So they don't really happen that often. But we do have to talk about it. So when you have a do-while loop like this, we perform BLK or block 1 first. Then we check, excuse me, then we check the condition C. If the condition C is true, then we go back to perform another block 1, and then we check it again. So the only difference between this and the loop before is when we check the condition. Do we check the condition first, or do we perform at least one iteration first? So this one translates pretty easily because we just simply perform block 1. And if the condition C is true, then we go back to label L1, which is all the way back here, right before block 1, so that we can perform another iteration. So the structure code looks like this, the flattened code looks like this, but they behave identically. So are there any questions? And this is all the control structure that I'm going to talk about. I will not talk about for loop in this class, because a for loop in C and C++ is really a while loop, except things get rearranged a little bit. Okay, the post operation becomes a part of the inside the parentheses of the for, and then you can have initialization also as the first part of the inside the parentheses. But other than that, it really is the same as a while loop, where you have pre initializations before the while, and then post operations right before the end of the block inside the while. So and for that reason, we'll only talk about the while loop and not the for loop. All right, so there doesn't look like there are any questions. If there are no questions, we're going to move on to section 4. In other words, but Jack, you haven't really talked about what about the condition C. What if C is a negated condition expression itself? What if it is a logical AND? What if it is a logical OR? What if it is a logical OR? On one side is a logical AND, on the other side is a negated logical AND, which inside is another logical OR, and blah, 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 blah. Okay? Well, now we'll try to figure out what to do when condition C is not something that is simple. So the first thing is 4.1. Now 4.1 says, what if we have not C, okay? If C is not true, we go to label L1. This is the original code. If this is the case, one way to deal with it is to introduce a new label L2. Now the label L2 is also called what I would call a continuation label, okay? Because L2 is simply here. The definition of L2 is here, which basically just means, oh, let's just, kind of continue the execution. Nothing exciting happening here. So let's check out these two versions of code and see if they behave the same. If condition is true, then not true is false, and we simply continue execution with whatever is after the if statement. If the condition C is true, we go to L2, and L2 is a continuation label, and we just continue with whatever is after this block of statements. So the behavior of the two pieces of code are the same. What if C is false? If C is false, then not false is true. Then we are going to continue execution at label L1, wherever label L1 is. Okay, so we are not even concerned about where label L1 is. We are just concerned about getting rid of the not in front of the condition. So what about here? If condition C is false, what's going to happen? Well, if condition C is false, we are definitely not going to label L2. And we continue execution here with a go to L1. So now we still end up continuing execution at label L1, wherever that is. So the two pieces of code would have the same behavior. Now, having said this, most of the time we can deal with negation without having to resort to something that is clumsy like this. It doesn't mean that it doesn't work. It simply means there are preferable ways to deal with negation. So we'll talk about this later on. We can use De Morgan's law and a few other tricks to get rid of negation. And section 4.2 talks about what if we have an or, okay? What if the condition that is leading to a goto is an or between two sub-expressions, okay? Well, that's actually pretty easy to deal with too, right? Because if C or D go to label L1, simply means that if C is true, let's go to label L1. Oh man, C is not true. What are we going to do? Then we check conditions D. If D is true, then we also go to label L1. So that's kind of how we get rid of logical OR as an operator in the condition that leads to a goto. So are we okay with section 4.2? All right. We do not seem to have any questions. Then we are going to move on to section 4.3, which is logical AND. So if the original one is if C and D, if they're both true, then we go to label L1. Otherwise, we continue execution. Then we translate that to the following. We basically say, well, since this is a logical and if I find that not C is true, which means C is false, don't bother to evaluate condition D or sub-expression D, because in a conjunction, if the left-hand side is false to begin with, the whole thing is going to be false. So we might as well just continue execution at label L2 right away. What if condition C is true? Well, if condition C is true, then condition not C is going to be false, which means we are not going to go to L2, which also means we will then evaluate condition D. So by the time we get to the second conditional statement, by the time we get here, we already know that condition C has to be true. So if condition D is also true, then we can go ahead and continue execution at label L1, wherever that is. Okay, so what if condition C is true but condition D is false? Well, if condition C is true, then not C is going to be false. We are not going to go to label L2. We continue on to the second conditional statement. But since condition D is false in this particular scenario, we are not going to go to label L1, so we fall through to the definition of label L2 and we just continue with whatever is at label L2. In other words, this piece of code has exactly the same behavior as this piece of code. And the advantage, even though we end up with more conditional statement with another label definition and more go-tos, we got rid of the conjunction. So the idea is to get rid of logical operators. All right, so are there any questions at this point? Okay, so we got some questions coming. This stuff is kind of boring, it's very, very mechanical. Yes, so then we recursively apply section 4.1 and we look at this whole thing and go like, okay, what can we do about this? Wait, it matches the pattern of section 4.1, so we will apply 4.1 to get rid of the negation. Does that make sense? Each time we finish with something, we basically go through all the rules again to see whether at least one of these 3 rules would apply, and then if it does apply, then we break it down and we break it down further. Until when? Until we don't see any negation, conjunction, or disjunction. All right. Okay, so moving on to section 4.4, which basically just talks about simple reductions. So the simple reduction is, if you see it is not the case that x is greater than or equal to y, you can just go ahead and replace the comparison with x is less than y. So this is kind of convenient because we got rid of the negation, but without having to go to section 4.1 and introduce new labels and a new go-to and stuff like that. Which also leads to now section 5. So section 5 talks about comparisons. Now you guys might remember when we talked about binary number comparison, I focus on one thing only. Okay, I focus on only whether the minuend is less than the subtrahend. I never said anything about equal to. I never said anything about greater than. I never said anything about less than or equal to or greater than or equal to. Why is that the case? Well, as it turns out, less than is all you need, okay? So if I only give you less than and possibly equal to, okay, because equal to we got the Z flag to identify equal to, which is kind of handy. Can we use these two to replicate, all of the other comparison operators? That's the question. So if I just give you x is less than y, then there's nothing to translate because less than is available. If I give you x is greater than y, then you reverse it so that it becomes y is less than x. If I give you x is less than or equal to y, then you break it up to x is less than y or x equals to y. If I give you x is greater than or equal to y, then you break it up to y is less than x or y equals to x. Just kind of reverse the x and y compared to the one right before. X equals to y is fine because we have the Z flag that can tell whether the minuend and the subtrahend are the same or not. And the way the Z flag works is already discussed in, I think, the previous class. By looking into the ALU, I kind of explained the mechanism of how the Z flag works. And the last one is, what about not equal to? Well, in this case, we have a negation, and then a x equals to y. So this negation is kind of unavoidable because the other way to express x does not equal to y is to use less than, because we can also say, x is less than y or y is less than x. But that's even more troublesome compared to using a negation on x equals to y. So that's how it works. All right. So do we have any questions all the way up to here? Because there's a lot of stuff covered already. Okay. The first part talks about how we can reduce structured C code into flattened C code. The second part talks about how do we reduce expressions, okay? How do we get rid of negation? How do we get rid of conjunction? And how do we get rid of disjunction? And then this part over here in section 5, we talk about what about comparisons, okay? Well, all we really need is less than, is the ability to confirm less than, and also the ability to confirm equal to. And then we have the logical operators, like we have the or, and then we have the negation. So we can utilize whatever that we have talked about before to also get rid of the or and also the not. All right, are we doing okay so far? Because there's really quite a bit of material covered up to this point. And we got some questions coming, so keep the questions coming because this is the only way to slow me down. All right, just do you don't even need equal to. Yep, I know, but since we have the Z flag, we can do it. Because even though so there's a balance between risk versus CISC. In other words, do we only want the least number of transistors so that we can do everything with only those transistors? Okay, that's the ultimate purist RISC design, RISC. So we can kind of shift gear a little bit and talk about RISC versus CISC, as opposed to, okay, we put in more transistors, okay, so that we can quickly and more time efficiently do comparison and check for equality. Okay, so in this case, it's all about checking for equality. So the answer is we don't want to be a purist. Okay, we don't want to be pure RISC, or we don't want to be pure CISC. So now I'm going to shift gear and talk about something that is really hard to ask in an exam, but nonetheless it is a very important topic. So it is the dilemma of RISC, RISC, versus CISC, CISC. Okay, so RISC stands for Reduced Instruction Set Computer, and CISC stands for Complex Instruction Set Computer. One approach, RISC, is to say, let's make the processor design as simple as possible, and we'll make up, for the simplicity of the processor by making the program, okay, making the assembly code a little bit longer and a little bit more convoluted. Okay, that's the RISC philosophy. The CISC philosophy, on the other hand, is to say, we can just put in a few more transistors here, and we can make this quote-unquote job or whatever function that we need to perform a whole lot easier. Okay, so instead of using 5 opcodes to specify this, I can use one single opcode to specify exactly the same operation. So that's the CISC approach, or the CISC philosophy. So now the question is, well, because people like black and white stuff, right? So people always ask, so which one is better? Well, the answer is always beginning with, it depends. Okay, it depends. So right now, I think RISC is getting a whole lot more attention because everything is driven by industry. Okay, it really has nothing to do with preferences, of personal preferences. So it's not about whether you or I or the consumers, prefer CISC processors, kind of like the AMD and the Intel x86 type processors, or whether we prefer RISC architectures like the ARM processors. RISC is, how about this? I just press the Enter key. So if I press just the enter key, you will basically find all the articles that you will basically need to read to talk about to understand this. So RISC is Reduced Instruction Set Computer, and CISC is complex instruction set computer down here. Okay, so what is driving? Okay, so the question is, what is driving people or industry to use one versus the other? That's the question. Because you might say, hey, with my Pentium 64-bit architecture, okay, with one single opcode I can do blah 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 blah, okay, a whole bunch of stuff, okay. And then when you look at a more purist type of RISC architecture, the ARM architecture is not, by the way, it's not very purist, okay. So if you want a purist type, you have to go to the gosh, I cannot remember the name of that thing. PowerPC is not that purist either. It's an architecture that UC Berkeley uses for instruction, but it also gets used by industry a little bit. But I cannot remember the name of that processor. So let's just look it up. Berkeley RISC processor. Okay, so I should be able to find it. It is used in certain printers, but I cannot remember the name of it. And there's nothing here that mentions it. Oh, it's called the MIPS processor. There we go. And it's the Stanford MIPS processor. Okay, there we go. So it's not Berkeley, it is, Stanford. It's called the MIPS processor. That one is a whole lot more purist compared to the other RISC processors. So the original question is, what drives, which one we should be using. So the scenario that I want to give you is you have a LAN party, okay? Because I know most of you understand what is a LAN party, LAN. You basically invite your friends to come over to play, video games so that you guys can be in the same room, so that you can scream and yell at each other and throw things at each other. While the team is starting to lose, you can start to blame on each other, like because you're sitting right next to each other, okay? So LAN party is fairly kind of common, I guess, before COVID-19. Now that we have COVID-19, unless you have a LAN party with your siblings and other people living in the same household, you probably do not want to have a LAN party with other people. So anyway, the idea is you have a LAN party. And let's just say that you have a fairly generous room that you can play video game. So let's say that's your bedroom, and your bedroom is reasonably sized, let's call that 12 by 12 foot, okay? So you have a 12 foot by 12 foot room, and if you put enough desks in that room or tables in that room, you can probably fit 4 people, playing video games, at the same together, okay? Let's make it 5, because let's just say that we are playing League of Legends and a few other games that require 5 people on the team. All right, so are we good so far? Is everybody picturing that you have 5 gamers in a reasonably sized bedroom? Okay. So now everybody wants to bring their own computers, right? Their own monitors, because people are used to their own setup and they don't want to use somebody else's setup. So now the question is, what is the power consumption of a kind of professional gaming computer that people would like to brag about? I know somebody's going to answer this question. It's going to be a hot room, yes, but I want the numbers, okay? So what is a typical power supply on a well-configured gaming system? I would call it 1 kilowatt, okay? So maybe the actual power consumption is only 700 watts, but we'll call it a 1 kilowatt, power supply. The reason why I kind of know the figure is because I just got a box that houses one single graphics card, and it hooks up to my laptop computer through Thunderbolt 3. So this way, I can, practice, game programming, using my laptop computer, which does not have a GPU. Okay, and that box comes with a 600 watt power supply, even though it's only intended to power up one single GPU, graphics card. So it does have, extra power to power up the laptop computer too. And we'll call that about 100 watts. Okay, so out of the 600 watts, 100 watts goes to the laptop computer itself, and then the other 500 watts are dedicated to one single graphics card. Okay, so that means out there somewhere, okay, either with AMD or with NVIDIA, they're making graphics cards that can potentially consume up to 500 watts. And then when you combine that 500 watts with a reasonable desktop processor, so if you're talking about the high-end i7 and i9 processors, and 32 gigs of RAM, a RAID hard drive array, or SSD array, and plus a whole bunch of LEDs, blinking and whatnot. 1 kilowatt is not an unreasonable estimate. Okay. So now you have 5 of those computers, right? You have 5 setups like that. And don't forget about the monitors too, because the monitors they're not really that significant, compared to the graphics card. But, when you add up everything, 1 kilowatt per person is a very reasonable assumption. So the first problem you run up against is your breaker will pop. Yes, because most breakers are only rated at 20 amps. So when you have a 20 amp breaker, you get about, if you push it, you get about maybe 2.5 kilowatts out of it. Okay, and then the breaker is going to pop. Okay, so that means, for this room, you will need at least 2 breakers, if not 3. So you're going to have to ask your parents to pay for an electrician to basically rewire the house and add, at least 2 more breakers to feed the outlets of that particular room. That's going to be expensive. And let's just say that that problem is solved. Okay, your parents are totally supportive of you becoming the next esports star, and decided, yeah, we're going to hire the electrician to install those 2 additional breakers. So now you can pump all the electricity into that room, no problem. No breaker is going to pop anymore. What's going to happen next? Okay, you plug in all 5 computer setups, everything is up and running. Cool. All right, so let's get into a marathon of these, of these network games. Okay. So now you have 5 kilowatt, output in terms of the power supplies, the monitors, and whatnot. Now, energy cannot be destroyed. Okay, you can convert energy from one form to another form. Like when you use batteries, in electronics, you're converting energy from chemical energy into electrical energy. And when you turn on a flashlight, okay, you're converting some of the chemical energy into light, okay, into photonic energy or visible photon energy. But the rest is actually wasted mostly as heat. Okay, so when we're talking about computing equipment, okay, let's say 1 kilowatt, most of that energy is wasted as heat. The only part that is not wasted as heat are the LEDs blinking, okay, and depending on which color of the LED, the efficiency can be fairly high, especially in when LEDs are the red ones and also the green ones and also the yellow ones. Those can be pretty efficient. And then you have the LEDs, as the backlight of the monitor. So we are talking about maybe, okay, 20 or 30 watts converting directly into visible light. Okay, the rest are all heat. So it's basically the same thing as, okay, so if you compare a hair dryer, okay, a hair dryer is rated at usually about 1.2 kilowatts or 1200 watts. Okay, so you can basically just kind of imagine that you have 4 hair dryers at the highest setting running the whole time in one single room, which is 12 foot by 12 foot in terms of the footprint. So what's going to happen after half an hour of gaming? In other words, if you turn on 4 hair dryers in a room like that for 30 minutes, what's going to happen? I'm gonna wait for Daniel's answer because I think it's gonna be entertaining. He stops typing. What's gonna happen when we have 5,000 watts converting mostly into heat? Well, I'm not even sure another AC unit is going to help. Okay, I haven't really done the calculation, but I think a single portable air conditioner is not going to be able to do it because that's a lot of heat. You can do it outside. You can do it in the backyard. So heat is an issue. Okay, so heat is an issue. So do you think this issue is only with gamers? Or do you think this is also an issue that Google, Facebook, all of these tech giants that run huge, gigantic data centers would also encounter? Of course they're going to encounter this problem, okay? Because when you have a room that is filled with rows and rows and rows of racks and racks and racks of computers, the density of computers to the size of the room is really high. So if you think we have a problem getting rid of heat in a 12-foot by 12-foot room with 5 gamers, that is nothing compared to the kind of problems that Google, Facebook, and other big companies that run data centers have to deal with. All the server rooms have those problems, yes. So now the question is, how does this have anything to do with the CISC versus RISC, discussion? Because it doesn't seem to have anything to do with that, right? Yep, even with a small server room has similar problems, okay? But Google wants to pack as much processing power into as little of a space as possible, okay? And it is not a problem of feeding enough electricity or power into that enclosure. It is about the problem of extracting the heat, okay? So now the problem is not about how much processing we can do per clock. It is a problem of how much energy do we need to perform the same operation. So the unit that is of concern here is called MIPS per watt. MIPS per watt. MIPS in this case, I think, is a fairly archaic term. It stands for million instructions per second. So we are looking at how much processing power we can pack into a unit of energy, and we want that to be as high as possible. So as it turns out, okay, when this is your focus, then RISC wins compared to CISC. Now, we don't really have to kind of think too much about that, okay? Because when you look at the specs of a cell phone or anything that is mobile, which one has an Intel i something processor in it? None of them, okay? The answer is none of them. You might have laptop computers with an Intel i something processor, but when you're looking at something that is wearable, something that is truly mobile, like a Fitbit, okay? Like an Apple Watch, iPhone, okay, and all the other smartphones, none of those would make use of an Intel i something processor or an AMD 64-bit. The instruction set is called the AMD instruction set as well, but none of them would use a CISC architecture because it takes more energy to get the same amount of computation done. Now, does it mean that those processors are slow? No, we are not even talking about how fast or how slow a processor is. We are simply talking about how much energy do we need to basically perform a particular kind of computation. So as it turns out, if that is the major concern, then RISC makes sense, okay? So now the question is, because I think it's good to keep asking questions, right? So the question now is, why is RISC better in this case? It's because RISC processors do not waste silicon. It does not waste transistors. So when you have a CISC processor, you basically have millions, okay, hundreds of millions of transistors. Okay, and most of those transistors at any particular moment of time is not doing something that is productive. Okay, they're just sitting around waiting to be called upon to do something. Okay, eventually. So, but they're also consuming energy because they're quote unquote sitting around, and most of the time they're making transitions, just unnecessarily. So as a result, with a CISC processor, with all those extra transistors that are for the most part not needed, they basically waste a lot of energy. As opposed to a RISC processor, which has very few transistors compared to a CISC processor, and yes, it's going to take a few more instructions to get the same thing done, but when it comes to energy wasted on transistors that are not used on the die, they are very frugal. Okay, RISC processors really do not waste energy on transistors that don't do anything useful. So that is the reason why RISC processors are basically the processors of choice when it comes to data center. And then we got some questions here. What would Apple chips be considered? Are you talking about the processor chips? Those are all RISC type processors. Yep. Okay, so I do want to kind of continue this discussion for maybe another few minutes or so before I kind of release the next lab and let you guys go. And I cannot quite remember exactly what I was about to say. Nope, no roll call. Let me think about this. Think. Oh, right. Okay, I remember now. So if CISC processors are so cool, okay, because they are very energy efficient and all that stuff, then how come your laptop and your desktop computers are still using the CISC type architecture? So I want you guys to think about that for a moment when I go release the next lab. So I'll give you guys a few moments to think about it. The next lab is absolute value, this one here. And once I'm done setting up this lab, I'm going to go back and see if you guys have any ideas. So the lab code is ABS. So the access code of the lab is ABS. And I'll make it due in a week. Okay. And once again, as usual, you want to get started on this one as early as possible, so we don't have to kind of rush, at the end. We don't have to rush a week from now to try to get it done. So save and publish, all done. Okay, ABS lab code. That is funny. Anyway, all right. So the question was, how come we're still using the CISC processors, even in laptop computers where energy efficiency is kind of an important thing? Well, there are several reasons. Number one reason starts with an M. Okay, so what do you think that is? Yes, it is money, but it is money for whom? Not us. Well, we are giving these corporations the money, but which corporation starts with an M, and it is it's the only reason why we are still using CISC processors. Yes, it is Microsoft. There we go. Monopoly would work too. It is Microsoft. Okay, so why is it Microsoft? In other words, can't we just switch to a RISC type processor even on a desktop or a laptop computer and be done with it? We can potentially save energy. We can reduce the amount of fans and heat sinks and whatnot. It makes the computer smaller and more compact because of that. It has to do with Windows, yes. So let's compare Windows and Linux. So one way to look at Linux is go to Debian.org, which is one of the many distributions of Linux. So what we want to do is to take a look at, okay, let's see if I can search for that too. So we want to look at Debian architectures. In other words, we want to know, what kind of architecture, what kind of processor architectures are supported by Debian, which is really just one of the many distributions of Linux. So we can look at this list here. Okay, some are unofficial, some are unsupported, but even if you just count the ones that are supported, you can see the list is relatively long. Okay, and this is just one distribution of Linux. It doesn't count, the kind of Linux that are in a research lab, and graduate students are porting Linux to those, experimental, architectures. So even with architectures that are published and commercial, Debian supports quite a few of those. Okay, what about Windows? Now, if you look into the history of Windows, it is not like Microsoft did not try. They certainly tried, but they never succeeded to support anything other than the Intel architecture. And now the question is why? Right? Because Linux is open source, which means people who ported Linux to all of these architectures, they don't get paid, at least not directly by anyone who's using Linux. Okay, so the question now is why do people port Linux to so many architectures and seemingly without too big of a problem, when Microsoft is saying, okay, our Windows operating system would only run on the Intel architecture and it's backward compatible all the way to the 80s. So why do you think that is the case? Well, that may be the size of it. I mean, if you look at some of the modern Linux distributions, they can take up quite a bit of space too. But the question is, why isn't Windows ported to different architectures? Okay, well, it has to do with development, yes. It has to do with compilers, okay? With GCC, which is the compiler for not only Linux but also for BSD and other types of free operating systems, the back end of the compiler can retarget new architectures relatively easily because it's a very modular design. Once you have a compiler cross-compiling to a specific architecture, then it becomes relatively easy to port Linux or FreeBSD to that architecture, because the percentage of an operating system that is written in assembly language, which means that portion is architecture dependent, is relatively small. Okay, at least with Linux. So that means Linux is easy to port to a new architecture, RISC or otherwise. Okay, and Microsoft never released the source code of their compilers, and the source code of Windows is actually proprietary as well. But I have a strong suspicion that it has a lot of dependency on the architecture. It was never made to be modular, and as a result, they could not retarget a new architecture easily. And that is the reason why Microsoft does not want Intel to basically say, we are not going to support the x86 architecture anymore because these newer architectures are far more efficient. Because Microsoft would not be able to sell their products if all the PCs make use of a new architecture and it is not binary compatible with Windows machine code. So I got a few points in a text area. So the vast amount of work makes it backward compatible. The amount of work is not on Microsoft, by the way. The vast amount of work is on Intel and on AMD, because those two companies have to manufacture the chips in order to let Windows run on those chips. And then the next one says, do you predict that Windows will die out as new components come out from ARM and other companies? Well, that's a very interesting question because a lot of things are moving onto browsers, right? So that's why we have Chrome OS and Chromebooks, because a lot of things you can now do without having to install apps. All you have to do is to go to a particular URL, and everything is running inside a browser. So as a result, what operating system you're running is not as important as before anymore. Windows 10, can I copy your homework? Windows 8, yeah, just don't make it too obvious. Well, that's the thing, because even upgrading from one version of Windows to another version of Windows can be a pain, okay? Especially if you skip a version, then it becomes a nightmare if you want to upgrade your operating system. It's just ugly, okay, if you want to skip a version in Windows. So the bottom line here, okay, the bottom line is in most situations, RISC is really a better choice, even for desktops and laptop computers. We're only using CISC because historically that's how Microsoft operating systems use, and because of certain limitations that is inside Microsoft, they cannot retarget a new architecture as quickly and as efficiently as open source software, and that's why Microsoft is pressuring the hardware manufacturers to stay with the Intel architecture, the old Intel architecture. Exactly. Yeah, it's all about money. So if you think about these larger corporations, a lot of times it is less expensive if they spend the money on lawyers instead of engineers. I mean, that's kind of the bottom line. I mean, they just want to minimize the amount of money, and it's easier to have an army of lawyers to, let's just say, fix problems as compared to hiring more qualified engineers to really solve the problem. Yeah, I'm not even kidding. I mean, there are historical records of all of this kind of stuff, and it applies to just about every single company in high tech. So those companies range from Microsoft to IBM to Oracle to Google to Apple and so on. I mean, why else do you think we have so many patents, right? I mean, patents are basically just ammunition for lawyers to use against, each other. All right, so that's the end of today's lecture. Yes, I know we are over by 15 minutes, and the lab is open. Okay, so the lab access code is ABS, as Aiden has already typed here. So go ahead and try to get started with this one early, and if you have questions, let me know. Oh, you're most welcome. Yep. Yep, I'm just old enough to remember a lot of things. Yes, I can certainly do that. So let me right click and pin. There we go. All right, so without any further questions, I will go ahead and stop my live stream. And good night, everybody, too. I'll see you guys on Thursday. And yes, it is election day.